Hello, friends. I am Michiel Darbari, founder and CEO of Aximize. And to our new listeners, welcome. To our old ones, welcome back. I have quite a personality in-house today, someone who's been in the industry for many, many years and has been involved in a range of foundational activities that are impacting all of us in the industry. Friends, I'm talking about Michiel Ligthart today, who is here in-house. Hi, Michiel. How are you?
Hi, Ashish. I'm doing fine. Thank you very much to have me on your podcast.
No, thank you for taking time out from your busy schedule to come and talk to us. I'm sure we have enough interesting things to cover today. I have been a user of Verific, which is where you are, and you've been with Verific for quite some time. But before we dive deep into Verific and what you've been doing currently, I want to actually talk about some of the fascinating things you've been doing and your journey towards science and engineering, if you don't mind. So where were you born? How did you get into engineering?
Okay, that's an interesting question, and I'm happy to answer. So my accent is Dutch. I was born and raised in the Netherlands, in Amsterdam to be precise. And in my earlier years in elementary school and high school, I always had an interest in physics and mathematics. Liked to tinker around with electronics. My father was a technician, was trained as a technician before he became more of a business person, trajectory that many people, of course, follow. Mm-hmm. And so I was guided, or at least there was the opportunity to do things like that. So after high school, I subsequently went to Delft University of Technology in the Netherlands, and I started studying electrical engineering. After I graduated there with a master's in EE, I got myself a job offer from a company in Silicon Valley. And we're now talking about the mid-80s, 1985, 86. So that was not that common that people would cross the ocean and move to the valley. And I thought it was a wonderful opportunity, as during my last 2 years of studies, I got involved in integrated system design, semiconductors, which were then still fairly new with 2 micron with IC width. Mm-hmm. And so that's how I crossed the ocean and ended up in the San Francisco Bay Area. I was employed by a company called Signetics, which later was acquired by Philips Semiconductors, nowadays known as NXP. And I was working in their research lab, doing specifically research on electronic design automation and testability. I then had the great fortune to be deployed as a visiting scholar at Stanford University here in the area, and that was a marvelous time. I spent almost 2 years there working with Professor Nanni de Micheli and his graduate students, and we worked on high-level synthesis. I was working also with people in Berkeley, UC Berkeley, Corey Hall, who were doing logic synthesis, program MIS. And that lay a very nice foundation for this new wave of electronic design automation that was coming in logic synthesis and optimization.
Right.
A company like Synopsys was founded at that time and powerhouse in the 25 years since. After a little while, I was approached by a startup company called Exemplar Logic. There they did logic synthesis for FPGAs, which was a brand new activity.
Which year was this? Which year was this? When you joined?
We were talking about 91.
I see.
So it was 5 years into my California adventure, and by that time it was not an adventure anymore. It was just a steady state. Coming from Northern Europe, I had come to love the California weather. The fact that I could wake up in the morning and see blue skies and knew it was not going to rain that day. So I went to Exemplar Logic, early employee on their R&D staff, developing logic synthesis for FPGAs. And now we're talking when Xilinx was still the Xilinx 2000 series, right? The 3000 series.
Oh, I see.
I would say, well, nowadays I look back at that and say, well, that was in the days that it was all still simple. I think if you look at FPGA semiconductors nowadays, they're quite complicated devices compared to those early days. It was also at Exemplar that I got to work for the first time with Rob Dekker, who is the founder and CTO of Verific Design Automation.
Right.
We recruited Rob. Like me, he's a fellow Dutchman, and he moved to California as well. And was another contributor on our technical staff there. And it was at Exemplar Logic that Rob was exposed for the first time to languages like VHDL and Verilog, and he became the point person over time in developing and maintaining the front ends at Exemplar. Exemplar was eventually acquired by Mentor Graphics, and I think we're now talking about 1996. And both Rob and I stuck around for a little while, and then we both, for several years even, but then we both left to do something else, and it was about 99. Rob left to became the founder of Verific Design Automation. I had left a little bit earlier for something completely different. I joined a startup company in asynchronous logic, which was a wonderful technical journey.
Which company was this?
The company was called Theseus Logic, and they had a technology called null convention logic, invented by Carl Fand. Very interesting technology. We managed to build a company, and the company had at the end a working semiconductor prototype. We had a working EDA flow, but unfortunately, from a business perspective, it did not really solve the problems that we expected it to solve. The expectations for asynchronous logic were great in less power consumption, and there's less need for power, regular power. But as I say, at the long term, the business was not there.
I see.
And so when that adventure came to an end, Rob had worked steadily on his business at Verific, and he asked me, he said, "Hey, Michiel, would you be interested in teaming up with me here and see if we can build this out?" And I said, "Well, why don't we give it a try?" And here we are, 16 years later, thriving business, 20 people worldwide. More than 75 active customers, which I think are happy customers. And what we estimate is more than 60,000 users worldwide through our licensees.
Right. So you're talking about now your current role at Verific, right? So
correct.
Right. So let's talk about Verific a little bit. So I've already been using Verific products indirectly because a lot of the formal verification tools I think use Verific. Tell us what is the actual core product that Verific builds? So for people who may not have heard of Verific, it might be a good thing to know.
Yeah, of course. So Verific is not a traditional EDA company in the sense that we do not have an end user product. There's no EDA tool that we sell, but instead we have built this building block, which is a system Verilog and VHDL and UPF parser and elaborators that we license to EDA and FPGA and semiconductor companies for use in their products. So, for instance, if you would be looking at the Xilinx and Altera FPGA design software, and you read System Verilog or VHDL in there, then actually that piece of software that takes care of that is provided by Verific. That is our core business, and it's also our only business. There's nothing else that we do.
Interesting how your core business is around something so foundational as a parser. And you mentioned System Verilog, and VHDL and UPF. But I'm just going back to some of the things you were saying earlier about when you started your career in high-level synthesis. And high-level synthesis is mainstream these days. And one of the things that people are also talking about is C to silicon. And what are your thoughts on that? And are you making any products that allow people to parse System C?
Well, I can start with answering that last question. No, we do not have any C++ parsers or anything like that. But indeed, in the early days at Stanford, the team that I was part of was building a high-level synthesis tool based on the language hardware C. Mm-hmm. And that was really an academic effort and research effort, so it never became a part of a company or an actual tool that people could use. And already in those days, I noticed that the moment that we wanted to be really sure that something was going to work well, we migrated more towards RTL descriptions rather than C descriptions for the chips. But hey, it was a research topic, so everybody had to learn. Since then, there have been many efforts in the industry to build high-level synthesis tools, mm-hmm. and some of them have been successful. For instance, if we look back many years, you may remember the efforts from IMEC in Belgium with the Cathedral project. Mm-hmm. And they were targeted towards a specific architecture. And in their case, it was DSP, digital signal processing.
Right.
And I think those were quite successful. But if people tried to do general high-level synthesis, did not always come to fruition. Although I think there are plenty of good products in the market nowadays, mm-hmm. but somehow they have not taken over the RTL design methodology.
Yeah, I mean it's certainly an evolving market and it's growing at a fast pace. I hear more and more companies adopting different facets of high-level synthesis. But let's come back to Verific again. So what is fascinating is that you said the only thing you do is focus on parsers for, let's say, 4 languages. And I'm quite amazed as to how many customers you've got just building parsers. And that too, like in terms of software, there's far more languages. And if you were in a market building parsers for C and Python and Java and whatnot, then you can imagine. But is this a big enough market? I mean, is this a sizable chunk of revenue stream for Verific?
Yeah, for us it definitely is, and but it's not a market segment that will ever take you IPO, right? As I mentioned, we're a 20-person company, and it's a really nice business for us, and we deliver a very good service to our customers. And quite often, I also look at us, okay, we have this product based on the IEEE standards, mm-hmm. But at the end, we're also very much a services company. We deliver a service to our licensees. They look at us as an extension of their own R&D. Uh-huh. In the early days of EDA products that were supporting Verilog and VHDL, mm-hmm. every company had its own software development team focusing on VHDL and Verilog implementation. implementations. And a couple of people, 4 or 5 maybe, you had to build test suites for it, and a lot of efforts were duplicated, and that was very costly. But at the same time, it also was a distinguishing factor. If you were able to deliver good Verilog support and your competitor was not, now that is a reason why a customer will select your EDA tool and purchase your EDA tool.
Right.
But over time, that differentiation started to disappear. And I think that is the market opportunity that Rob Decker noticed and said, hey, everybody has to do it. They all have to do it from the same specification, which are the IEEE standards. It's not really easy to do it. So there's significant effort involved. So let's see if I build this, if I can sell it to multiple people. And that clearly became, that was a true insight.
Right.
And so you get to a point where good support of the input languages, Verilog, VHDL, and later on system Verilog, almost becomes like basic hygiene. If you bathe every morning, nobody will compliment you on the fact that you don't smell. And the same thing is if you support your system Verilog and your VHDL, fine, it's now anticipated, accepted. You cannot come in the door with poor support in that area.
So Verilog, and to a large extent system Verilog and VHDL, they do change a bit, and there are features coming in every year or 4 years. But the major chunk of the language doesn't really change that much. How do you actually go about putting together a test infrastructure to see that your parser isn't malfunctioning? How do you find any bugs in your parser? That was one of the questions that I was.
So when a new language version of the language comes out, the first step we do is a line-by-line comparison between the two, and the committees help with that by providing redlined versions. And we have our own engineers, including myself, on some of the IEEE committees. I'm part of the System Verilog committee. We're on the UVM committee. We're on the UPF committee. So when the LRM comes out, we make that line by line differences. For every difference, we write a few test cases, and that's how we do our development.
Right.
Then, of course, we have all the test cases from the previous versions that we continue to run as regressions, and that way we grow our regression suite. Over now, we have, I think, almost 80,000 tests in the Verilog and System Verilog sphere.
I see. So a follow-on question. At Aximize, we thrive on formal verification, and one of the foundational things we use is a system Verilog assertion. So does the Verific parsers parse the assertions as well?
Absolutely. Yeah, absolutely. We parse the entire IEEE 1800 language.
Right.
Everything is parsed. It's put in a parse tree, which is a syntax extracted parse tree. And from there, people can do different kind of elaborations.
So now I have my next question. So assuming that you were, because parsing is basically, you're sort of dismantling the syntactic structure of something and putting it together in an abstract form for follow-on processing. Is it possible that you could parse an assertion into two different abstract syntax trees? Or could you actually perform an optimization step after the parsing and you can actually have an optimized representation as well? Or every parsing step has a canonical abstract syntax tree and there's not much you can do?
You definitely can optimize the assertions once they're in the abstract syntax tree, but that is up to our customers.
Right, that's what I
to actually do that. Because some of them want to keep it as is, direct representation of the original syntax,
yeah.
and others like to have it in an optimized
Right.
format. One option that we do have for customers that like that, we allow them to actually synthesize the assertion.
Mm-hmm.
And that is where we built a finite state machine out of the assertion.
Uh-huh.
And, that's not widely used by our customers, but
Right.
But some people do that. They like to take a look at that now. And that's a complicated piece of software because an assertion can rapidly expand in memory and use up an enormous amount.
Depends on what you do with that assertion, of course. So it makes a lot of sense. So in terms of your challenges year on year, what are your challenges? Are you seeing a lot of rapid SoC development cycles actually making some of the things you do on the parsing end, on the front end, a lot harder for you or easier for you? For example, this whole UPF thing is now an add-on from a low power point of view. But I could imagine other verification concerns, design feature concerns such as functional safety or security may actually bring in more language constructs, for example, into system Verilog. I mean, what kind of challenges are you grinding on year?
Well, things that we definitely run into are runtime and memory consumption.
I see. Okay.
On the large SoCs.
Right. Mm-hmm.
Some of our licensees, we mentioned Jasper Gold beforehand.
Uh-huh.
Their customers run gigantic designs, so we constantly they get pushed by their customers, and we get pushed by them to improve on runtime and memory. And obviously, wherever possible, we do so, and you get the position in a situation where actually the two R&D teams really start interacting as one. We are bouncing off ideas to each other and say, hey, will this work and will that work? And some of them are very specific to the implementation of that particular EDA tool, and others then can be implemented inside Verific, and more of our other licensees have the benefit of that as well. Definitely a challenge is that we do not only deal with the IEEE LRM, but we also at times have to deal with competing implementations by other tools.
I see. Okay.
And we mainly look then at the three biggest simulators and some of the leading synthesis tools.
Right.
And these places have also quite often a long history of how they did things in the past. And they are not quickly going to change their front end, even if they know that it is incorrect. They say, well, this is the way it is. And then you can be a little bit of a hard nose and to say, well, it's too bad. The LRM says ABC, so we're going to implement ABC. But the end user, that doesn't help for the end user, right? Because they said, well, but we cannot change our RTL. So we get to the point where we at times have to introduce compatibility switches so that we can match behavior by another tool. And you cannot do that proactively because there is no description of that, right? You really have to wait until it's reported from the field, and look at it and see what we can do about it. Now, the big three EDA companies are very much aware of that as well, and they're very supportive of us. So we have access to the simulators. So whenever we have these mismatches, we have the availability to check it ourselves and confirm with the customer that this is indeed the case, and see what we can do about it. So it's all in good spirit, but it is a challenge, and that makes it where I previously said it's sometimes feels like we're in a services industry.
Oh yeah, I mean, I
because
totally,
it's not just
yeah,
one
totally
product
get it. Yeah.
that you shrink wrap and sell.
I mean, practically, your challenges you're describing are larger scale engineering challenges, and this is what makes engineering fun, right? So even though your product may be stable, you're now getting performance issues on large designs or feature issues with respect to things not working on for some other customers who may be using competing tools and have different models. I wanted to share something interesting you may not know as a user of formal tools. I've seen Verific compile a 1.1 billion gate design in formal for me, where I was doing some functional verification. And it was quite an interesting experience for me, having to grind off a terabyte of swap was consumed on my machine, and about 128 gigs of RAM was very easily consumed. I think it took about 45 minutes to compile a design of that size. Interesting things happen in verification as well, but everything begins from parsing. So if I can't parse, I can't do anything. And I've certainly seen a big improvement in performance as an end user of tools. So I totally understand all of the things that you were mentioning, because
and I very much appreciate that feedback, by the way, because that's something that we sometimes miss because we do not deal directly with the end user.
Yeah.
So I was not aware that you have a billion gate design that you still was able to run in 45 minutes. I think that's great feedback.
So actually the limit,
you shared that.
Yeah, the limit was not reached in terms of Verific necessarily. I think the formal tools that I use actually have a 32-bit counter. And I think when they do reset analysis, as the design was growing in powers of 2, after a certain point, the number of gate count went over 4.2 million, and they started counting negatives, so they couldn't do reset analysis. So in terms of the methodology side, I wasn't limited. I think in terms of compilation, Verific was able to compile even bigger designs than 1.1 billion gates. But I just couldn't do formal on that because of these little naughty issues. But hey, that was a very useful insight into verification. I was just looking at the clock, and it looks like we've been having a lot of interesting chat. So in the interest of time, let me wrap up our chat today. What I would like to ask you, Michiel, is, a lot of our listeners are young professionals, undergraduate students. And for someone of your background to have come out of Holland, traveled to US, and done so many different things in electrical engineering and computer science, what would be your 5 tips if you wanted to give to the younger generation? Whether it could be career advice or engineering advice or anything else that they could take home, what would that be?
Ooh, those are of course always difficult because things change. But I would say always keep looking for something that is new and exciting. I have come to the conclusion that quality of work is extremely important.
Uh-huh.
I have also seen between myself and some of my colleagues of the same generation that some of them stayed very technical, and some of them, like myself, moved more into a support, management, marketing, administrative role. And now that I'm 60 years old, I wish I'd stayed more technical. So that is, I would say, my biggest advice for the young generation. Whatever your career brings you, make sure that occasionally you tinker around with technology, write some Python scripts. Keep that knowledge handy. That's the one thing that I miss the most.
Cool.
From the career.
Mm-hmm. Any other tips you would like to give?
No, I think that's plenty for now.
Okay. Thank you so much. I think what you've offered today is a very interesting insight into a small company of 20 people with thousands of users of your products designing something foundational such as a parser, which actually affects almost the entire semiconductor design verification ecosystem. So it's a fascinating story, and I'm sure people would love to find out more about Verific. Although, as you said, a lot of us are not direct customers of Verific tools, and it's the EDA mostly. But thank you very much for your time today, Michiel. Much appreciated, and we'll stay in touch.
It was a pleasure to chatting with you, Ashish.
Thank you very much. So listeners, I hope you enjoyed our chat today. Do let us know by emailing me at info@aximize.com or subscribing to our YouTube channel if you haven't already done that. So keep listening and keep learning as we are, and we'll be back shortly again. Thank you very much.